Okay, we're done. Okay, so the closure property is a set of numbers is said to be closed under a certain operation if the answer is in the same number set. So when you first started to learn numbers as a kid, okay, you started with basic numbers. What numbers did you start with when you learned how to? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are our first set of numbers. Okay. So we're gonna have to make this, we're gonna make it really big. So you want a small one kind of in the middle. Let's see, undo. Okay. So I'm gonna draw this little box here, like so. And then in it, these are what we call natural numbers. Okay, it's the first numbers we learned. 1, 2, 3, dot, dot, dot. Okay. Okay, hold on. So our next number set is integers. Okay, and integers now include negative numbers. So we have -1, -3, still 0, 1, 2, all that continued on. So integers include whole numbers and natural numbers, but something different now is negatives. Okay, so now let's see. We know that integers are now closed under adding because 2 plus 3 is 5 and 5 is an integer. 2 times 3 is 6 and 6 is an integer. 2 minus 3 is -1 and -1 is an integer. So integers are closed underneath adding, subtracting, multiplying. Let's try division. Okay. 2 divided by 3 is 2/3 or 0.6 with a line above it. Are those integers? Those are not integers. Okay. Integers are only whole numbers, ones we can't with, but negatives as well on the other side. Okay, so now we have what we call a new number set that we needed, so they can be closed under division. Okay. And this number set is called rational numbers. Now, rational numbers, again, include all of our integers, all of our whole numbers, all of our natural numbers. But now we're going to throw in fractions and decimals. So 2/3, 0.6 with a line above it. Okay. So we're super good now, right? We're very excited that we have all those. Okay. Okay, rational numbers, the definition of a rational number is it can be integers, but it can also have fractions and decimals that repeat. Okay, so 2/3 is a decimal that continues to repeat over and over again. 0.66666 goes on forever. Okay, if a decimal doesn't repeat, then it's not going to be a rational number. Okay, let's show you what those are. So we have rational numbers are closed. If I add two rational numbers, I get a rational number. If I multiply two rational numbers, I get a rational number. If I subtract two rational numbers, I get a rational number. If I divide two rational numbers, I get a rational number. So adding, subtracting, multiplying, dividing. But now we go to more complicated operations, like square rooting. Okay? We have the square root of 5. If you have a calculator right by you, plug into your calculator the square root of 5. Yep. Huh? No, that's half of it. That's not the square root of it. 2.23, wait, 2.2360679, and it continues on forever. Even though your calculator doesn't show all of the decimals, the square root of 5 isn't a rational number because the decimal never doesn't repeat and it continues on forever. It's a 2. Let me erase that.
Wait, so why don't they just put the line thingy over it?
Because it doesn't repeat. The line thing shows that that number repeats over and over again.
So it's kind of just like pi?
It's kind of like pi. It goes on forever. So that is what we call a irrational number. Irrational numbers do not include rational numbers because it's the opposite basically of a rational number. So we put this right here. Right next to and we call this irrational. Okay, and irrational numbers are like the square root of 5, the square root of any non-perfect square, square root of 21, square root of 7. We have that special one that pi is also an irrational number. Okay, irrational numbers are numbers that are fractions or decimals that don't repeat. So they're radicals. Okay, they're decimals that go on forever. So pi is an irrational number, and all the square roots of non-perfect squares are irrational. And within that, so irrational and rational numbers go together in this whole amazing thing. Another box, yes. These are all called real numbers. One more.
Oh, are you using big boxes? I mean, big numbers?
Yes.
Yeah, that's what I meant.
Okay, so these are all real numbers. Numbers that I can show you exist. Okay. Any questions over that? And it includes all of this stuff. It includes rational, irrational, integers, natural numbers, whole numbers, all of it. Those are all what we call real numbers. We get to this thing where we have a problem when I plug into my calculator the square root of a negative number. Everyone, if you have a calculator, try and plug in the square root of -4. It says error, right? There's something wrong with that. Because a square root is what number times itself gives me -4.
-2.
Okay, let's try that. Is -2 times -2, what is that? +4. They need to be exactly the same because it's a square with the same length of sides, right? I can't have a side length of a -2 and a +2 and then it be considered a square, right? It's not a square. Okay, so this is where we come up with imaginary numbers because we still need to be able to do the math, but it's really not a 2 here. It's going to be imaginary. So that's all the way over here. We have our new set of numbers that aren't connected to real numbers at all. They're the opposite of real. They are imaginary. Shh. These are imaginary numbers. Imaginary numbers are I. You will see an imaginary number and they'll use I as imaginary. It is the square root of -4. It's the square root of any negative number is an imaginary number. And I will tell you that's right here.
So basically, every negative number is error, right? It's an imaginary number.
Is if you, yes. If you have, it has to do with solving quadratics that you're going to need those imaginary numbers.
Oh yeah, so like when we have the square root,
Mm-hmm. No, you put imaginary.
but don't we use imaginary numbers in calculus?
Yes, you will.
That's what my dad told me.
Okay, we're back up here. Okay, so we can extend our number system of numbers to include not only real numbers, but also imaginary numbers. An imaginary number is I, is the number whose square is -1. So I equals the square root of -1. Okay, if I have I squared, then it's basically taking the square root of -1 and I square it, right? The square root of, and I square it, those are inverse operations of each other. So they basically undo each other. So what will I get left with?
Error.
Not 1, -1. Yes, it would, but we are smarter than our calculators. Okay, or we're going to be now. Okay, we have, yes. So the square, so I squared is -1. And you have to memorize that. You need to memorize it. Memorize. Very important. So when we're simplifying, here's how we'll do this. Okay? The square root of -2, all you do, this is like the square root of -1 times the square root of 2. The square root of -1 equals I. So you have I times the square root of 2. The square root of -1 is I. Yes. Yes. We'll get there. So this here would be the square root of -1 times the square root of 25.
So I is what?
Shh. The square root of -1 is I. In class, what's the square root of 25? 5. So times 5. We raise our hands if we have a question. So our solution to this is 5I. Okay, the next one is 3 times the square root of -1 times the square root of 36. Okay, again, the 3 doesn't change. We times the square root of -1 is I. And class, what's the square root of 36? Times 6. Okay, so we get 3 times 6 is 18, and then I. Any questions over that? Okay, negative square root of -72. This is like -1 in front times the square root of -1 times the square root of 72. -1 is just -1. The square root of -1 is I. Do I know the square root of 72?
Yes.
What is it?
8.4.
Okay, we're not going to plug in our calculator. Do I know the square root of 72? No. Okay, so we're just going to leave it as the square root of 72. So -1 times I is just -I square root 72. If we can't simplify, we don't simplify. Imaginary and real numbers together make up a complex number. Okay, so this right here is what we call a complex number. It has an imaginary part and a real part. So the A is the real part and the B is the imaginary part. Any questions over that? Okay, so now we're going to simplify some complex numbers. Okay, if you look at the complex numbers, the real number is always in front. The A is the real number and the BI is the imaginary number. So we always want to make sure that the real number is in front. Okay, so that's going to be the 6 is going to move to the front. Okay, and then plus, what's the square root of 9, class?
3.
3, and because it's negative, I need an I. So this is my complex number, 6 plus 3i, because it has an imaginary and a real part. Okay, the next one. Again, I need to have the -4 in front. So make sure you take the -4, put it in front. Do I know the square root of 8? Nope. But I do know that it's a plus square root. Oh, sorry. It's got the negative, so I need the negative and the I in front. Let's try that better. It doesn't look as nice as I would like it to be. So this is I, and then square root 8.
Wait, why is the square root now?
Because the 8 doesn't have a perfect square. I could simplify the square root of 9,
Oh.
but I can't simplify the square root of 8. So I'm just going to leave it as a radical 8. But I do need to take the negative out of it. Yes.
When you can find the square root, the I is after the number, but when there is square root.
Yeah. You could technically put it at the after, but it looks like it's inside the radical. And you want to know that's not inside the radical. So that's why we put it in front. Any other questions? Okay, so do J in your pairs. Simplify that for me. We're going to have the 4 plus I. You can have one I. You don't need it, though. It's just going to be 4 plus I. Any questions over that? We're all good? Okay, adding and subtracting complex numbers are just like adding and subtracting polynomials. You're just going to combine like terms. Okay, imaginary numbers go together and real numbers go together, just like x squared goes with an x squared and x goes with x. Okay, so that's all we're doing here. So 5 and -2 are like terms. Okay, they're both the real part of our complex number. So 5 and -2, they're opposite signs, so I subtract and get 3. 7i and 6i, they're also like terms. So 7 and 6 are both positive, so they're the same side. I add them and I keep their sign. Any questions over that? Okay, next one. You're subtracting here. So we have to distribute the negative. Okay, so I'm going to have the 12 plus 5i, and then plus negative times 2 is negative 2. A negative times a negative makes that positive I. Then we're going to combine our like terms. 12 and negative 2, they are opposite signs. So once again, I'm going to subtract and get 10. 5i and 1i, they are the same sign. I'm going to add. This is like a 1 in front of it. So 5 and 1 is 6 i's. Any questions over that? Okay, did you do the next one really quickly? What did you get for your solution?
I got 4 plus 11i.
Good job. 4 plus 11i. We got this. Okay, next one. Now we're multiplying. Okay, multiplying. Yes, it's our box thing again.
Good stuff, right?
Okay, oopsie, I don't want a yellow box.
Yeah, I'll become a skater.
That was kind of. Okay. So this side length is 8 plus I. This is 2 plus 7i. And then we're just going to multiply. Remember, we're finding the area of each of those individual boxes. So 8 and 2, 8 times 2 is 16. So the area of this box is 16. Then I times this length of 2 is 2i. Then 8 and 7 is 56 i's. And then finally, I times 7i is 7i squared. Okay, let's review. Going to go back to that first page. Everybody go back, turn it over. What does I squared equal? Yes. Negative 1. Okay, so we need to use that here. We're going to write that right down here back on that page. Okay. I squared equals negative 1. Okay, so we're going to have to use that. So here, that gives me 7 times my negative 1. Does that make sense? Okay, so I'm just substituting in negative 1 for the I squared. So this becomes actually 7, or negative 7. Does that make sense? Okay, so that's this. Yes, because I squared, I'm just substituting for the I squared, negative 1, because that's what I squared equals. Okay. Not yet, because we have to combine our like terms now. So now I have my like terms. So I'm going to combine my like terms. So 16 and negative 7 go together. They're opposite signs, so I'm going to subtract and get 9. And then I have 2i and 56i. They're both positive, so I'm going to add them and get 58i. Okay, and that's my complex number. Any questions over that? Yes.
If it goes to the third power, then say it was 7i to the third power, then it would just be positive 7.
It would be negative 7i. Because I squared, because I cubed is I squared times I, right?
Yeah.
I have an I squared that can change to negative 1. So it'd be 7 times the negative 1 times that leftover I. Don't worry, we're not getting cubes. But that's how it would work. Okay, next one. Okay, that's super easy because you're just multiplying two numbers. So you guys try that. You should have one number solution.
The multiplying these make it squared.
Mm-hmm. Okay, let's see where we're at. When you first multiply them, you get negative 2 times 5 is negative 10, and I times I is I squared. Once again, my I squared equals negative 1. So I'm going to get negative 10 times negative 1. So that just gives me positive 10. Because a negative times a negative is a positive. Any questions over that? Okay. Next one, we're going to do our box again. Okay, because this is squared, I have two of them. So I have 3 minus 6i and 3 minus 6i. What's 3 times 3, class? 9. Oh, good. Negative 6 times 3? Negative 18, and it has an I. And that same thing over here. 3 times 6 is negative 18i. Okay. Okay, and then a negative 6 times a negative 6 is a positive 36, and I times I is I squared. But I'm going to move that out here because I do know it's 36 now, and I squared equals negative 1, so this is going to be times negative 1, which now gives me a negative 36. Okay. Okay, then we're going to combine all of our like terms. So I'm going to have my 9 and my negative 36 as negative 27. Is that right? Okay. And then I have negative 18 and negative 18. I'm sorry? Oh, I didn't. Thank you. This is I squared here. Okay, but do we all follow okay? Yes? Yes? No. Oh, no, we do 27? 9 and 36, I subtract 9, 16, no, 7, 27. Yeah. It's all right. We've all multiplied wrong in our lives. Okay, so that is my simplest form there. No, because you're just counting how many eyes I have. I have 36 here, and I have 18 here, and I have 18 more. Together, I still have 18 or 36 eyes. Okay, next one. We have to do one step before. We have to simplify the radicals. What we're going to do here first. So we're going to do 3 plus, okay, what's the square root of 4, class? 2, but it also has that negative, so we need an I with it. Do the same thing here, 5 minus, class, what's the square root of 9? 3. And again, it has that negative with it, so it needs the I. Okay, now I'm going to have you guys multiply those in your pairs. Just make sure you're watching your negatives and your positives on those. Class, quiet down, please. Follow along. Make sure you have this all the work worked out correctly. 3 plus 2i, and this is 5 minus 3i. I see some of you guys not putting the signs when you're making the box. Make sure you put the plus 2. Make sure you put the minus 3i, because it's going to make some mistakes if you don't. So this should have been 15. This should have been 10i. This should have been negative 9i. And this should have been negative 6i squared, which then becomes negative 6 times negative 1, because I squared is negative 1, so my positive 6. Then I can combine my like terms. 15 and 6 is 21. And 10i and negative 9i, they're opposite signs. I'm going to subtract and get positive I, or 1i. You don't need the 1 in front of the I. It's assumed. Any questions over that? We're all good? Okay. How do I get I? 10i and negative 9i. Okay.